So we're calculating some eigenvalues and eigenvectors, and those sound really cool now, but we'll see how cool they are as we go along. And so remember, we've got our friends here and Bartlett, and we have Ed, and Bartlett's going to have Ed rate these potential mates so we can find out if there's underlying factors in his mate choice to see how he's doing. So what he's going to start out with is a correlation matrix, which we already said earlier is the basis for principal components analysis calculation. And so in this matrix, you have the connection, obviously the correlation between smart and smart is 1 because that's the same variable. And so the diagonal of this correlation matrix is always going to be 1. And sometimes you'll see covariance matrix, which is what factor analysis does, but that's different. And then the correlation between smart and attractive was 0.67, so you can make that connection there. And obviously 1 here, and then we'll see this negative correlation between attractive and crazy. And then we have probably a not significant negative, but also negative correlation between crazy and smart. And then the rest of these are repetitions. You see the 0.67s, the negative 0.10s, and then the negative 0.29s, and then the 3 1s. So that's the basis of it. But now what we've got to do is find what's called an eigenvalue. So an eigenvalue is kind of like really what a principal component. It's finding a number that kind of underlies this matrix right here and can help help us find that point or that line that's below these factors. And so the first thing you do is you're going to subtract what's called lambda from the diagonals of the matrix. And I don't recommend you doing this at home. It's a pretty tedious process. I'm not even going to do all of it here. And then you've got to do something a little bit crazier to be able to do some of this calculation. We're going to take this first line of this matrix here, and we're going to put it actually outside of the matrix, and then we're going to take the second one and put it outside also. And that's going to help us to calculate out this equation to be able to find the eigenvalues. And so the way that works is it's going to be done in rows. So you're going to multiply this part of the matrix times this part of the matrix times this part of the matrix. Same thing here. 0.67 times negative 0.29 times negative 0.10, and so on. And then you're going to do the opposite. You're going to do the same thing with the opposite direction. So negative 0.1 times 1 minus lambda times negative 0.1. 1 minus lambda times negative 0.29 times negative 0.29. And then you see why we had to put the rows outside of the matrix. 0.67 times 0.67 times 1 minus lambda. This creates a pretty complicated equation. But when you factor it out, it looks kind of like this. And so what you would do is solve this equation for 0 to help us find what is that lambda. But it's not just one variable. It's going to be there's going to be multiple numbers that could solve the equation. And so that's what the eigenvalues are. So there's going to be more than one, and as we have three variables in this principal components analysis, there's going to be 3. There's always going to be the same number of eigenvalues or principal components as there are factors that you put in. Doesn't mean they're all going to be interpretable or you're going to use all of them. It just means they are going to be there when you look at an output. So here's our eigenvalues. The highest one is 1.76, and we have 0.93 and 0.3. And so what those are, and if the best way that I've seen to think about them conceptually, and then next we have to find what's called an eigenvector. So if an eigenvalue is a point, the point that represents the variance of that principal component, an eigenvector is that line that is drawn that encompasses the most of the variance. So the way that you're going to do that, or that you would do that if you were a computer and doing this analysis, you subtract the largest eigenvalue from each of the numbers in this matrix, and then you're gonna bring in what's called a scalar, which is this variable here that has these variables and try to get this equation to equal to 0. Again, really complicated stuff, requires a lot of equations, so I'm not going to do them here. But when you solve it this way, you're going to get, and this one right here was just the first eigenvalue. You'd have to do it for each of the 3 eigenvalues. But when you do that, you're going to get this matrix right here. So this row is going to be the eigenvector for factor 1. And so, well, so that's going to kind of help us to see what these values are, where this line could be, because you can't draw a line with just one point. You need multiple. You need at least 3. And so that's where those eigenvectors end up coming into use, and kind of just to help you understand it a little bit visually, and to see how these things, you can see how they will help us to find these principal components.